we are going to start something new today. Okay, I need everyone to be paying attention. We're going to do something new. It's going to sound scary, but it's not. So we are going to do a very simple, basic introduction to calculus. So calculus is a branch of mathematics that you do not need to worry about yet. But what we are going to do is look at some of the basic ways that we can use calculus so that we're ready to use it next year. All right. So I promise it's not actually scary. It's actually pretty easy this year, but we need to have this easy foundation so that we can do challenging things next year. All right. So you're going to see some weird terminology, some new sort of ways of writing stuff. Don't worry too much about that at the moment. Again, you'll learn more about it next year. What we do want to learn is just how to do some basic calculus. So we're going to start with something called derivatives. I can't remember how to spell derivatives. How terrible is that? Derivatives. Derive, derivative. Derivative? That doesn't look right. Derivative. It's not a U. Derivative. Let's go with that. Derivatives. So we are deriving equations. It is also called differentiation. All right, differentiation. So what we're really doing here is we're going to take an equation, we're going to alter it so that we can find new information. Okay, can we close our laptop, please? All right, so let's start with the most easy thing in the world. So y equals 2, sorry, that's not what I meant to write. Y equals x squared. This is a graph we're used to dealing with, but there are new things that we can do with this. Josiah, can you put that down, please? All right, so we are going to take the power and bring it down the front. Then we're going to subtract this power by 1, which just leaves 1. So that is the derivative of this. Now, the way we write that is not by saying y. The way we write that is by saying dy dx. So dy over dx equals 2x. The derivative of this function is 2x. Don't worry too much about that yet. Let's do some more examples that'll make more sense. If I say y equals 3x cubed minus 4x squared plus 6x. All right, let's derive this. So dy dx. I am going to take the power here, bring it down in front and multiply it by whatever number's there. So I get 9. Then this power is being subtracted by 1. I'm going to do the exact same thing for every term. So here I bring the 2 down here and multiply it by this number. So I've now got 8. And then I subtract this number by 1. So I don't need to write 1 though, do I? So this is just 8x. Same thing here. Bring the power down. What's the power? It is not. It is 1. Thank you very much. If you can't see it, it's 1. So 1 times 6 is just 6. But if I subtract the power, 0. Now, from our index laws, what is anything to the power of 0? Good. So if x to the power of 0 is 1, this is just 6 times 1, which is just 6. So this bit disappears. That is the derivative of this. Let's do another one. All right, let's look at this. So dy dx. You will notice I no longer have powers in descending order. I'm skipping some. You're allowed to do that. You don't need to have all the powers. So what would my first term be? Good, 50x to the power of 4. This 5 comes down here and multiplies, which gives us 50. And then we subtract 1 from the 5, which leaves us with 4. What about this second term? 12x cubed, right? So we bring the 4 down, we times it, which is 12. Subtract 1, we get 3. What about this bit? minus 12x. We bring the 2 down, multiply it by the 6, and this becomes 1. Now, the constant just disappears. It's got no power, so it doesn't fall into the derivative, right? It's going to disappear. So anytime there's a number without an x or without a variable, we ignore that, and it doesn't exist. So this is the derived function of this. So let me write one down, and everyone's going to have a go at doing it for me. So get your pen and paper out, and please give me this derivative. It is long. There's lots of terms, but you just do them all separately. Have a go at writing down the derivative of that equation. I'm going to try and move this. Nope. How do I get the hand function on this one? Watch the signs. That's right. All right. So dy dx. So the derivative of this should be 4 times 6 is 24. So 24x cubed minus 9x squared plus 12x plus 4. That's all I should have. This is disappearing. Hopefully we all got that. Now I'm going to show you one way to use calculus. Bless you. Yeah, it is recording. All right. So what we're going to do now is derive an equation. One of the things that derivatives do is tell us, so let me give you an example. So if I said that y equals 4x cubed minus 3x, the derivative of this is what? 12x squared minus 3. This, okay, so this is important. This is what it actually means. This is the equation of the gradient of that function. What does gradient measure? What does it measure? Steepness, okay? Rise over run is only true for a linear equation, okay? But the gradient measures the steepness of a graph. If you've got a curved graph, how do you find the gradient of this? Okay, the tangent finds the gradient at one point. The problem with this graph is yeah? Okay, the problem with that is, though, you're only getting the gradient for one point, aren't you? Like, you're right, but that doesn't give you the gradient of the graph. It gives you the gradient at one point. So the problem with a graph that moves around like this is the gradient is always changing. If the gradient measures steepness, the steepness of this graph is constantly changing. So that's why we have an equation that means that the gradient is always changing. So we can only ever find the gradient at a point. Unlike a linear equation where the gradient is consistent, it goes up at a consistent rate. But curvy graphs don't do that. So what we can do with derivatives is find gradients at certain points. So let's have a look at how we do that. Yesterday, we did it by finding a tangent line, right? Which is one of the ways we can do it. But drawing graphs takes time, doesn't it? And as you noticed, you've got to be pretty accurate with drawing a perfect tangent line. Otherwise, it's not going to work. Whereas we can do this algebraically and actually get a perfect answer. So if I had this and I wanted to find the gradient at this point, this is the only number I care about, right? I only care about the x coordinate. What I'm going to do is put x into my derived equation, and that will tell me my gradient. So 12 times 1 squared minus 3 is 9, right? This is 12 minus 3. That means the gradient when x is 1 is 9. So what we're doing is just finding a gradient at a point. So that means it's pretty steep at this point. Let's do that again. So if I said y equals negative 2x to the power of 4 plus 2x cubed minus 4x. All right, I want to know the gradient at negative 2, 3. So the first thing I need to do is derive this equation. So dy dx is, let's derive this. What's the first term? Good. Plus 6x squared. Minus 4. Excellent. All right, so this is my derivative. I only care about my x coordinate. So what I'm going to do is I'm going to put negative 2 in place of x. So I've got negative 8 times negative 2 cubed plus 6 times negative 2 squared minus 4. So what's negative 2 cubed? 8. Careful. Negative 8, right? It's a cube. So it goes 2, negative 2, positive 4, negative 8. What's negative 8 times negative 8? Positive 64. What's this number here? 6 times what? 4. So that is 24. And then I've got a minus 4. So this is 64. Whoop, not quite. 64 plus 24 is 88 minus 4. Okay, so the gradient, when at this point, the gradient is 84. Right? That's a crazy high number, but that's allowed. Do you see what I'm doing? That's all we have to do with calculus.